That's Peter Lawson. All right, well, it is 3:10. I'm Dr. Stephen Click. I welcome those of you who are in the room and who have joined us virtually. I appreciate you taking this time out of your day. I know the students appreciate it. For those of you that have not been to a presentation before in senior design, I just want to give you a quick understanding. After each student presents a section of the report and it's time for them to trade who the next presenter is, there'll be about a 1-minute pause. Don't think that anything's wrong. That's to give our evaluators an opportunity to write comments down, finish their evaluation before we start the next person. So just be aware that we will have that pause and nothing is wrong when it happens. We also, you notice that I took my mask off when I got to this point, and that's because this room is spaced so that the individual at the front desk is allowed to take their mask off while they're presenting, so you actually get to see faces. Please don't be concerned. If you're in the room and worried about it, you can certainly back up. But the spacing has been set so that it is not a problem. And then mentors, I just want to give you a couple quick reminders. First of all, our sliding scale of grading, that what was good enough for an A the first time was only good enough for a B the second presentation, and is really that borderline C now because we expect our students to have improved. And then also we are on this time schedule that we've been having to work all semester, and we've added the fact that I like to give 5 to 6 minutes at the end for parents to ask questions. So just be aware, try to pick your most important questions and work with those. And then if we have some extra time, you can ask more, but just be aware that you have a little bit less time this round than usual. So those are all of my announcements. And so I'm going to put my mask on and turn it over to the group. If you all will give me time to get seated, that would be awesome. And then I'll just point and you can go, all right? Cool.
Would you like for me to minimize this as well?
You may, yes.
To that. Yeah. Hello, everybody. I would like to welcome you to our final presentation for our bridge replacement project over South Mill Street over the Buffalo River. Okay, the group presenting today will be Allison Howe, myself, Ethan Crabtree, Kayla Truman, Nicholas Lawson, Ravi Patel, and Sarah Roten. Our project is located in Perry County. Perry County is labeled as a distressed county, which means it has a poverty rate of 30% or higher. Here's a more in-depth view of our project location and the project parameters. The project consists of a bridge that is 695 feet long with a sufficiency rating of 47.5%, therefore warranting a bridge replacement per TDOT standards because it does not meet the 50% mark. Here's a view looking downstream from atop the bridge, and here is a view looking upstream also from atop the bridge. I know you will probably not be able to see this too well, but this is our Gantt chart. This shows each discipline in the black boxes and the tasks they had to complete before they could finish the next one. Outlined in red up here is the critical path. That will be discussed more in depth in the next slide. Here's the logic chart, which is also showing the path of tasks that need to be completed and so forth. Outlined in red is also the critical path. I would now like to turn it over to Allison Howe for the first portion of our transportation discipline of this project.
may begin.
Thanks, Ethan. I'll now begin the transportation portion of this project. To start, this is our traffic control plan we made using Google Maps. Utilizing Squirrel Hollow Drive and Bethel Road, we found there was an approximate 15-minute detour as a max. Based off of this small detour, we determined that we could close down the bridge during construction to minimize costs. Shown here is our transportation parameters that we used. A design vehicle of an SU-40, shown here on the right, which is a 40-foot single unit truck. We decided on this SU vehicle based off of the residential neighborhood area and that a large school bus could be approximately 40 feet long. We chose a design speed of 40 miles per hour, a function class of a rural minor collector roadway, as well as 2 ADT values, which is the annual average daily traffic flow. The first being 1340 vehicles per day, which is in the base year 2023, the expected in construction date, as well as a second ADT value of 1610 vehicles per day for the 20-year projected year. For our main road, South Mill Street, our proposed typical section was adapted from RD11 TS2. We decided to use the 2 existing 12-foot lanes, but extended the shoulders to 4 feet. For our side roads, Riverside Drive and Hadley Circle, our proposed typical section is shown here. This was adapted from RD11 TS1. We decided to utilize the 2 existing 9-foot lanes, but increase the shoulders to 2 feet. Shown here is our horizontal alignment that we have proposed. South Mill Street center line, which is here in red, did not change. However, as I zoom in to the intersection of Riverside Drive and Hadley Circle, so you can see it more clearly, Riverside Drive center line did not change as well. However, Hadley Circle did. The reason for this was based off of skew angle deficiencies as well as side triangles, which Nick will discuss in further detail later. Shown here is the corresponding curve data based off of the horizontal alignment as well. I'll now hand it off to Nicholas Lawson to complete the transportation portion of this project.
You may begin.
Thanks, Allison. I will continue the discussion of the transportation portion of this project. As Allison mentioned earlier, the Hadley Circle was realigned due to side triangle and skew angle deficiencies. The existing skew angle for Hadley Circle was 45 degrees. This was far less than the minimum value specified in the AASHTO Green Book of 75 degrees, warranting the realignment. Additionally, a side triangle analysis had to be performed to determine if the intersection had adequate safety. Here are the side triangles that were drawn up. The small orange circles represent the driver's eyes on the roadway. For the minor roads, Riverside Drive and Hadley Circle, these were placed back 18 feet from the edge of traveled way, and they were centered in the lane. Additionally, using TDOT RD11 SD3, the 2 other orange eyes were placed 390 feet away from the intersection. Of the 4 sight triangles that were analyzed, only one was found to be deficient: the left turn from Riverside Drive onto South Mill Street, represented by this sight triangle line here. This is a Google image which shows the view when a driver is turning left from Riverside Drive onto South Mill Street. This shows visually the deficiency in sight distance. The driver cannot see very far up South Mill Street. This is a ground profile that was cut using the sight triangles as previously discussed. The sight line in red was drawn using a driver's eye height of 3.5 feet specified by AASHTO. The sight line intersects the ground line, confirming previous suspicions that there was an inadequacy here. Earthwork is going to be proposed to clear away this obstruction and mitigate this problem. This is the final vertical alignment for South Mill Street with 3 vertical curves, 2 sag curves, and 1 crest curve, curve 3. These curves were designed using K values from AASHTO tables, and the lengths of these curves were determined from controlling AASHTO equations. These equations are based off of stopping sight distance, comfort and appearance for minimums, and drainage for a maximum length. It may be noted that curve 3, the vertical crest curve, was not within the construction limits. The reason the construction limits were placed at this point is because the existing horizontal and vertical alignments match up exactly with the proposed horizontal and vertical alignments. Here are the vertical alignments for the minor roads, Riverside Drive and Hadley Circle. A sag curve was proposed for Riverside Drive to minimize the breakover angle between Riverside Drive and the shoulder of South Mill Street. Without the vertical curve, you would have a breakover angle of 12%, exceeding the maximum of 9% set in AASHTO. Hadley Circle has a crest vertical curve to transition between the 2 grades. Again, the lengths and the K values were determined using controlling AASHTO equations and tables. Cross sections were cut from the vertical alignment of South Mill Street. Earthwork volumes were calculated using these cross sections by comparing the proposed slopes outlined in color with the existing slopes outlined in black. These areas were then multiplied by the lengths between each station to come up with the earthwork volume. This is the first portion of the transportation cost estimate. The average unit prices were determined from the TDOT average unit prices database, and the quantities were determined using the typical sections, as Allison mentioned earlier, multiplied by the length of the roadway, not including the length of the bridge and not including the length beyond the construction limits. Excavation volumes, again, were determined as previously discussed from the cross sections, but a quantity was also included for the estimated excavation required to clear the site distance problems. The total transportation cost estimate came in at a little over $300,000. I'll now hand it over to Sarah Roten to discuss the environmental portion of this project.
You may begin.
Thank you, Nick. I would now like to discuss summarize the permits required for this project. The first permit being the National Pollutant Discharge Elimination System permit. This is classified as our construction general permit and includes our stormwater pollution prevention plan. The second permit is the Aquatic Resource Alteration Permit. This is required because our project is classified as a rural minor collector. The third permit is the United States Coast Guard permit. This is required because the Buffalo River is classified as a navigable waterway. I would now like to discuss the best management practices for the erosion prevention and sediment control measures. Here's an example of an enhanced silt fence. This fencing will be placed along the perimeter of the disturbed area of our project. We have approximated about 3,500 linear feet of fencing will be needed for our project. This will need to be replaced throughout the duration of our project. Here's an example of a rock check dam. These rock check dams will be placed within the wet weather conveyances shown in orange. This is used to reduce the flow of the stormwater runoff from the roads. Here's an example of a riprap apron. Similarly to the rock check dam, this is also used to reduce the velocity from the stormwater runoff. We have identified one place where this is needed for our project, as shown in yellow on the screen. This is needed because the stormwater runoff discharges straight into a wet weather conveyance, which we need to slow down the velocity of the stormwater runoff to reduce the erosion, prevention in this area. Here's an example of a temporary construction exit. We have identified 4 places where this is needed, 2 north of the bridge and 2 south of the bridge, as shown in yellow. There is approximately 3.3 acres of land that will be disturbed throughout the duration of the project, and since this is less than 5, this classifies our project as needing 2 stages for the erosion prevention and sediment control. The first being the clearing and grubbing stage. This includes land clearing and initial major grading operations. The second and final stage is the construction stage, which takes place after all the final grading process has been completed. I would now like to discuss the roadway drainage for our project. All of the drains were analyzed in a program called HY8, which is a culvert hydraulic analysis program. The Q values were obtained for all of the pipes, and I'll discuss how we obtained the values for the flows. The C value was taken from the Chapter 4 TDOT drainage manual. We came up with the I from the NOAA PFD server, and the C was calculated in MicroStation to find the acreage discharge to each of the pipes. Here's a sample calculation of the Q50 and Q100 flows. The Q50 serves as our design flow, and the Q100 serves as our check flow to ensure that the water is not overtopping the pipes or the embankment area. Those values were plugged into the HY8 model to obtain the figure as shown on the screen. The embankment area is shown in brown. Now it's kind of hard to see. And the culvert barrel is shown in black. This is a 24-inch culvert barrel. And the flows are shown in blue and red. All of the existing drains were plugged into the HY8 model. And in black are the existing drains. And we have determined that these are acceptable for the proposed roadway alignment and the proposed bridge design of our project. I will now pass it to Ethan Crabtree, who will be discussing the remainder of the environmental portion of this project.
You may begin.
Thank you, Sarah. I will now begin to discuss the HECRAS modeling software used to perform a hydrologic analysis and hydraulic analysis of the Buffalo River. HECRAS stands for the Hydrologic Engineering Center for River Analysis System. It is a design software that is developed by the U.S. Army Corps of Engineers. In this presentation, I will discuss the completed models, which are the natural model, the existing bridge model, and the proposed structure model. To begin using this software, we obtained LiDAR data, which stands for Light Detection and Ranging, which we obtained from TennesseeGIS.org. This allowed us to see the low-lying lands, the existing structure, and then the elevation changes with respect to the land. I know you probably cannot see this too well, so out of exaggeration, I have darkened the cross sections, which are in dark green, and then the interpolation values are in the light green, right beside each one. There are a total of 5 interpolation values in between each cross section. There are 6 total cross sections, 3 below the bridge and 3 above the bridge. Each are spaced 150 feet apart from the previous one. The river is flowing from left to right on the screen. From that, we were able to get some cross-section data of the natural model. At first, using the land use land cover, we had chosen the Manning's N values to be 0.05, 0.03, and 0.05. Later, we discovered that that was not correct, and I will discuss that further on in the presentation. Shown, you can see the water levels for the 50-year, 100-year, and 500-year design flood elevations. Next, using the natural model that was built, we were able to input an existing bridge, the bridge currently in the project. The cross sections are the exact same. Water is still flowing left to right on the screen. Shown here is the specific 100-year design flood elevation, water surface elevation. That came to 488 feet, while the low chord of the bridge was at 491 feet. Therefore, we are not overtopping, or there was not any water being obstructed by the bridge. As I mentioned before, the Manning's N values were changed due to the land use land cover to 0.1, 0.03, and 0.1. As shown in the figure above, you have the 100-year existing bridge 3D model. You can see here we had messed up with the bank stations, and that was then corrected, and it had been used in the proposed design, which I will show you here soon. Lastly, we have the proposed bridge design, which was designed by Structures, was also put into that same natural model and adjusted accordingly to their design. Shown at 490 feet is the 100-year design flood elevation, and then the low girder or low chord is 493 feet of the proposed design. Therefore, we are not overtopping the bridge and not causing any excess forces and any obstructions, and the Manning's N values remained the same for this portion as well. Lastly, here's the 3D 100-year design flood elevation for the proposed model. Here you can see the design flood and the floodplain in which it lies, and the corrected bank stations. Lastly, I would like to discuss the environmental cost estimate. Originally, we had permitting, and we have the 3 permits that Sarah had mentioned. Those totaled up to $2,500. And then most of our cost was used in erosion prevention and sediment control. We had used an enhanced silt fence, and we had accounted for doubling it because of replacement during the construction. So that is why we have 7,000 linear feet for that, which totaled up to the total environmental cost estimate to be $107,100. I will now pass it on to Kayla Truman for the first portion of our structural discipline in this project.
You may begin.
Thanks, Ethan. I will now begin the structural portion of our project with the proposed stationing and superstructure design, and then Robbie will finish up with the substructure design a little bit later. But first, I would like to reintroduce the existing structure, which is displayed on the screen. It is a 695-foot-long bridge with 21 spans. It has a sufficiency rating of 47.5, indicating a total bridge replacement. The dashed line represents the existing ground profile. Now I'll begin the discussion of the proposed structure. After collaboration with the transportation discipline of this project, we decided on a total bridge length of 705 feet, and we have decided on 6 equal spans of 117.5 feet. The stationing is displayed on the screen. The gray boxes indicate the start and end of the bridge, and the green boxes indicate the proposed pier locations. The bridge will begin at station 104 plus 35 and will end at station 111 plus 40. Now I will transition into the substructure design. The majority of our calculations and designs were conducted in leaf bridge concrete and confirmed through hand calculations. Displayed on the screen are the loads that were selected for the design and analysis of the superstructure. Some of these include loads from earthquake, vehicle live loads, and wind loads. Robbie and I are very grateful for this software as it computed over 1,400 load combinations. Displayed on the screen is the proposed deck and girder design. The out-to-out width is 34.42 feet. This accounts for 2 lanes, 2 4-foot shoulders, and 2 parapets. As specified by AASHTO, the girder depth must be at least 4% of the total span length. This resulted in the choice of bulb T 63 girders. Additionally, we will have a final concrete strength of 9 KSI for these girders. Also, our current designs suggest a 9.25 girder to girder spacing with a 3.335 foot overhang. Now I will discuss the deck reinforcement. Displayed on the screen is the longitudinal reinforcement. This steel runs the entire length of the bridge. The top row will consist of 12-inch spacing and located 3.5 inches from the top of the deck. The bottom row has a 9-inch spacing and is located 5.5 inches from the top. As I change to the next screen, the transverse reinforcement will be added to the figure. The transverse reinforcement runs from parapet to parapet, side to side across the lanes. The top and the bottom will both have 8-inch spacings. This reinforcement will be placed on the outer edges of the longitudinal reinforcement to create a mat inside the deck. All of these bars will be US number 6 bars. The deck will experience both negative and positive moments. The negative moment will be 8.03 kip feet per foot, and the positive moment will be 12.82 kip feet per foot. These were generated in leaf bridge concrete and were also confirmed through hand calculations. The capacities exceed the ultimate moment that the deck will experience, therefore indicating an adequate design. Next, I will discuss the strand pattern for our pre-stressed precast concrete girders. Again, this was generated in leaf bridge concrete and the inputs are displayed on the screen. We decided to use 6/10 low relaxation 7-wire strands. Additionally, we have decided to use a combination of both draped and straight strands. Shown on the screen is the strand pattern generated in LEAP with some adaptations. As previously discussed, there will be a combination of both straight and draped strands, and the draped strands are indicated by the green and purple boxes. The green box, which consists of 4 strands, I will refer to as Group 1, and the purple box, which consists of 2 strands, I will refer to as Group 2. The draped strands will be held down by hooks at some point along the beam, and then will rise a set height. Group 1 will rise 54 inches, and Group 2 will rise only 22 inches. Shown on the screen is the strand pattern from an elevation view. As I previously mentioned, the draped strands will be held down by hooks along the beam, and the location of these hooks will be 40% of the precast length. This results in a total length of 46.1 feet. Therefore, located 46.1 feet from each end of the beam will be the hooks where the draped strands will start to rise. I would like to note that this figure is not to scale. Here is a zoomed in picture of the strand pattern at mid-span. The bottom row will consist of 12 strands located 2.5 inches in reference to the bottom of the girder. The middle row will again be made up of 12 strands and will be located 4.5 inches from the bottom. And lastly, the top row will be made up of 4 strands, located 6.5 inches from the bottom of the girder. To conclude the strand pattern design, we will have 22 straight strands, 6 draped strands, with a total strand count of 28. Additionally, the fabricator will need to know the initial pull value, which is 1,230 kips. This was outputted in LEAP, but again was confirmed through hand calculations. Additionally, with these girders, we must check for deflection, and LEAP outputted a total deflection of positive 0.353 inches. For the positive deflection, that indicates an upward deflection, and we must make sure that there's enough room for this deflection to occur. Our haunch is set at 2 inches, therefore there's enough room for this to occur, indicating an adequate strand pattern design. This will conclude the discussion of the superstructure, and now I'll pass it off to Robbie to start the substructure design.
You may begin.
Thank you, Kayla. I will now continue the structures portion of this project. I will be taking care of the substructure design as previously mentioned by Kayla. I will be talking to you about the design of the piers, the abutments, and then finally I will conclude with the cost estimate of our project. So here we have a figure of our pier. At the top we have the pier cap, and at the bottom we have the pier column supporting it. We have decided to go with a design of a single shaft hammerhead design for our piers. The reason we chose a single shaft design instead of a multi-column is because a single shaft provides a larger lateral load capacity for our piers. This larger lateral load capacity will help in unpredictable loads. These unpredictable loads could be the floating ice or debris. For this specific column, we have a 18 foot tall column with a width of 100 inches and a depth of 60 inches. One thing to note on this slide is that for the next couple of slides, we'll be focusing on the column. So here we have the column reinforcement. This was probably one of the harder aspects of our project because it took a lot of trial and error to meet adequate design. These parameters that we had to meet will be shown in the next slide, but as a preview, they are like moment capacity, shear, and torsion. For this column reinforcement, we have decided to use 14 number 11 bars in the X direction, as well as 8 number 11 bars in the Z direction. For the lateral bars, we have decided to use US number 3s spaced at 12 inches. All of this reinforcement will then be placed 4 inches away from the outer edge of the concrete to provide for clear cover. As you can see here, these are the parameters that I previously mentioned. Here we have the location of the top of the column and the bottom of the column. For right here, we have the ultimate axial load acting on the column, as well as the ultimate moment in the X direction and Y direction. Here we have the moment capacity of our column. Taking our moment capacity and dividing by our ultimate moment, we yield a 3.28 ratio for the top of the column and a 2.34 ratio for the bottom. This may seem as an over design, but per ASHTO's requirements, a minimum amount of steel is required for our column. This minimum steel is 67.5 square inches, and what we have provided is 68.64 inches squared. This shows that this column is an adequate design. Next, I will be talking to you about the pier cap's geometry. The pier cap will span the entire width of the bridge, as previously mentioned by Kayla, which is 34.42 feet. It will have a maximum height of 108 inches and a minimum height of 60 inches. It will also have a depth of 70 inches and will taper off to 10 feet, hence the hammerhead design. Here we have the pier cap reinforcement. Here in blue, we have the main bars, and in purple, pink, we have the stirrups. For the top row, we have used 13 number 11 bars. In the second row, we have 7 number 11 bars, as well as the third row, which will also have 7 number 11 bars as well. For the stirrups, we have decided to use number 6s spaced at 6 inches. In the bottom, we have our capacity for our shear divided by our shear ultimate. This shows that it is, the factor of safety is 1.44. This shows that this pier cap is adequate for design. Next, I would like to talk to you about the design of our abutments. Here we have the abutment piles. We had to determine the number of piles for our abutment before we could design our reinforcement for the abutment. We have decided to use HP 12 by 53 for our piles. Using lead bridge concrete, we were able to determine a total vertical service load acting on our abutment. Assuming that that load is evenly distributed among all the piles, we get a total requirement of piles to be 7 piles. The spacing of these piles were determined by placing the pile in line with the exterior gutters, and then spacing the rest evenly after that. So then we get a total space, or a spacing of our piles to be 4.625 feet. Here we have the geometry of our abutment. I would like to note that for the next slide, we will be looking at the abutment beam, which is outlined here in this pink. This is what we will be focusing on for the design of our abutment. Here we have the design of our abutment for our reinforcement. Using lead bridge concrete again, we had to figure out the vertical load, but at the strength limit state acting on this abutment. We have also assumed that one of the piles would fall out and provide no support for our abutment. This is more of a conservative approach, but this will help in the design. So doing that enabled us to get a total moment, ultimate moment of 676 feet. Using reinforcement steel for our abutment, we have 5 number 7s at the top and bottom of our abutment, as well as 2 number 6s in the middle. This provided a moment capacity of 777 feet. Then taking the ratio of the two, we get 1.15 for our factor of safety. This shows that our abutment is indeed a good design. Now I'd like to finish it up with the cost estimate for our total project. So here we have the cost estimate for our superstructure. It is broken up into the elements of the superstructure, as well as the material description, the average unit price, as well as the quantity. Here, the total superstructure cost is a little over $1.8 million. The same was then done for the substructure. Here we have it broken up into the elements of the substructure, as well as the material, average unit price, and quantity. The total substructure cost estimated to be about $580,000. Here we have the total project cost estimate. It is broken up into each discipline, and the total project cost for our bridge replacement over Buffalo River is $2.8 million. I would now like to take this time and thank our professors for all their help on this project. Dr. Kay, Mr. Waters, Dr. Huff, Dr. Baidu, and Dr. Click, as well as our mentors, John Pennington and Harrison Bruce. Here are our references. I would now like to open it up for any questions.
Okay, so John and Harrison, we're going to start with you all. We have a total of 350 and we have until 420. So if you could keep your questions to about 15-ish minutes total for the group. We're going to go back and we're going to start with Ethan, and we will do questions from both the introduction and his technical section later before we switch. Okay, so it's y'all's floor.
All right. First off, good job, Ethan. I thought the introduction went well. I didn't really have any comments jotted down for the introduction. I thought you covered it pretty well. Before I jump into the technical side, Harrison, do you have anything to add to the introduction?
Nothing to the introduction. I thought you covered it really well. You've done it great the whole time. Overall, I just want to say good job to all of you. And I'll tell y'all individually, I'm sure. But I thought y'all killed it. So
Thank you.
go ahead with technical if you want, John.
All right. Yeah, on the technical side, I might have missed it, but did you show a change or comparison between the water surface elevation between the existing and the proposed model?
Yes. Do you happen to have a slide number for that?
I didn't see it, so I didn't write down the number. You might have had it, but I missed it if you did.
Yes. Okay. There is the existing structure and the water surface elevation of 488.
For the 50-year?
Yeah, for the 100-year design.
Okay.
The existing bridge, and then for the proposed bridge, it went up to 490 feet.
Okay.
It's the 100-year peak flood.
Okay. Good deal. Sorry, I missed that. I guess you could summarize it all, just a comparison, maybe side by side.
Okay.
That's probably what I was looking for. It looks like you counted for the proposed piers and the proposed abutment, it looks like. So that's good. At first I was going to ask, so slide 49. So you pointed out the issue at the top of bank point.
Yes.
But you corrected that and showed us the correct version on slide 52?
Yes.
Okay.
Right.
Okay.
Yeah, right there.
Good. I was just going to ask before I saw slide 52. It's like, why not reprint it? But
Yeah.
good job. What design methods did you use in your model as far as energy equation, momentum? You know what I'm talking about in HECRAS?
Not necessarily. Can you rephrase that?
When you run the model,
Yes.
there's different methods you can pick. If you're not familiar with it, that's.
I'm not familiar. No, sir.
Okay. Well, I think that's all I have for you, Ethan.
Okay.
Good job.
Thank you.
Yeah, I don't have a ton to add either. I think you did a great job. I thought all your, images looked really good. I liked you did it, and it was in Sarah's slides too, where you kind of overlaid over the standard output that HECR has and HY8 gives you, made it a little bit more readable. I think that was a good decision.
Thank you.
That's all I've got. I think you did a good job.
Thank you.
All right, let's move to Allison.
All right, Allison, good job. Let's just get into it. Let's see here. Slide 12. I saw that you guys did fix it typical to look like the one for your project. And you quickly mentioned that you're matching 12-foot lanes, but decided to use 4-foot shoulders. Do you know, why did you choose 4-foot shoulders?
We decided on the 4-foot shoulders. One, it was included in the project scope, but also it matched the TDOT standard drawing. Okay,
so you're bringing the corridor kind of up to standard to a degree, I guess?
Yes.
Okay. And then your intersection, I'm not sure what slide number it was, where you showed the Hadley Circle coming, yeah.
15 or 14?
14, I guess.
Okay.
Okay. First of all, I wanted to say, yeah, it's good showing the legend and the existing roads and everything. One little thing would be to add the bridge. And then on the intersection itself with the improvements and getting your sight distance, was there a alternative to look at tying the intersections together, like a little bit closer?
Yes, we did look at that alternative as well, but we found with there's a property here in the corner, and so to meet the skew angles and sight distances, we found that this was a safe alternative.
Okay. All right. And then on your traffic control, it looked like it was one of your first slides, if not the first. Once again, this is a good plan. It's going to work. I'm a little confused by the yellow, but I think it might be my fault.
So we changed the yellow to the yellow color just so it could be seen more clearly for the PowerPoint slides.
Okay, I got you. All right. Good job. I guess that's all I've got for now.
Thank you.
Yeah, I don't have a ton either. I think you did a great job. I think you're having the typical sections called out specific for this project helps quite a bit. All your figures looked better. I think y'all really improved on that. My only thing that maybe a little ticky-tacky is the first slide was traffic control, which just didn't, for me, I would like to have some kind of recap of, just what we're doing on this project instead of jumping in straight to traffic control, because that may be something that you want to kind of have towards the end. But other than that, I think you did a great job, and I don't have anything to add other than what John said. So.
Thank you.
All right, let's move to Nick.
All right, and good job, Nick. Just jumping into it, slide 19. I had a couple comments. So, good aerial view. This doesn't appear to be your final design, though. Am I right?
Yeah, that was an oversight on my part. We did not include the realignment of Hadley Circle.
Okay. Because that's a good example of the intersections tying together, like I was saying earlier. But then your proposed is ultimately to curve it in to fix the skew and tie it kind of apart, right?
Yeah.
Okay. So just make sure we're, clear on that for future reference. Just make sure all the slides are consistent. Slide 22. So one thing we've been kind of hitting at all along is clearly labeling your begin and end construction limits. And so you've kind of done that for the end, it looks like. If you're able to end there, I guess if you wanted to, you wouldn't have to do any more proposed vertical alignment design beyond that point.
Yeah, so we designed the vertical curve there and then determined later on we could do the construction limits. That's kind of how we did it. But
okay. And in going back to plan view, your site triangles, all the distance you need to clear and excavate to get your site distance, you're sure that you're going to be able to end before station 117?
yes.
Okay. And you briefly spoke over the earthwork calculations using the cross sections. What method exactly did you use?
I use the average end area method.
Okay. Good deal. And then for your side road cross sections, I didn't see typical for those. Was that typical the same as South Mill Street?
So we did include Allison referred to the typicals earlier for side roads in South Mill Street.
Okay, I might have missed the slide for the side road typicals. I apologize.
Okay.
All right, that's all I have.
Yeah, good job, Nick. I thought your profiles looked better. Like John said, you may want to, for the begin and construction, but with all the curve data is there and all the stations and everything is there, so that looks a lot better. Cross sections look good. Can you go to slide 22 real quick? So you've got your slopes out to 4 decimal places on there, which just in general, we like to kind of have those at nice, even numbers. It helps the contractor and everything. So that's, may want to clean that up a little bit, and then on slide 19. So like John said, this isn't your final design, but you may have mentioned it, but I may have missed it. How far off the main line are those little dots that represents the driver?
So for the side roads, the dots are set back 18 feet from the edge of traveled way.
Yeah, just checking. That's all I've got as far as technical goes, and I think you did a good job.
Okay, thank you.
Okay, Sarah, and then John, if you can shorten up by a question or so that we make sure we keep moving.
Okay.
Asking the hard one, but just one less.
All right, let's do it. First, good job, Sarah. I like seeing the more erosion control devices, and it looks like you picked a lot of ones you'll definitely need. The slides are really good. I did want to ask if you think you might be needing turbidity curtains or anything like that in the river.
That's something we hadn't considered, but something that could be looked into.
Okay, and then lastly, can you go to how you calculated your Q values?
Mm-hmm.
I had a question about your intensity.
This one?
Yeah, that one right there, I guess. So the I value is the 0.29 and the 0.33?
Yes.
Okay. Is that, how did you come up with that?
So we took those values from the Chapter 4 TDOT drainage manual, and then we also referred to them in NOAA PFD server, and those values came out identical. So that's how
on the NOAA site, did you look at it relative to depth, like in inches per hour?
Yes.
Or okay. I would just double check that. That seems really low.
Okay.
Your values, your Qs are extremely low, but
Okay,
So I think the I value might be off potentially.
okay.
That's all I've got.
Good job. Like I told Ethan, the HY8 model looks really good. Looks, with the HECRAS and everything, I think it looks really nice. A little bit easier to read than what HY8 standardly puts out. Can you go to slide 28? Back at the beginning. I may have missed it. Did you say the ARAP?
Can you say that one more time? You cut out there for a second.
Did you say why the ARAP permit was needed, the Aquatic Resource Alteration Permit?
Yes, because our project is classified as a rural minor collector, which is in our scope, we chose this because it specifies it in the verbiage of the permit.
Okay. So, okay. And then one more, can you go to slide 34 real quick? So you mentioned the riprap aprons. Why are those needed?
So in this particular location, it's needed because this culvert discharges straight into a wet weather conveyance, and we're just trying to slow down the velocity of the roadway runoff and before it discharges into the Buffalo River.
What was your velocity coming out of that pipe, if you remember?
I think
It seems like with those really low Q values that you wouldn't have enough velocity to warrant riprap apron.
okay. Those were our Q values coming out of that particular pipe. So,
Well, you may want to double check what velocity warrants that apron. But
okay.
And then I think you did a great job.
Thank you.
All right. Already been up, so I'll bring this to Kayla.
All right, Kayla, you did a great job. I thought that all the slides were really impressive. It was super easy to follow. Unfortunately, I'm not much of a structures guy anymore, so I apologize for not really having any good questions for you at this time. But I thought it was easy to follow. The slides look great.
Thank you.
Yeah, so I'm kind of the same way. I think you did a great job. I think all the diagrams looked really nice. They're very easy to read. I could tell what was going on, even with no bridge experience. So I'm not going to have any technical bridge questions. I don't know if Dr. Huff is hiding in there somewhere. He might have some more.
I'm sure he's got some brewing up there.
But I don't have anything. I think you did a great job.
Okay, thank you.
And that brings us to Robbie.
Hey, Robbie, good job. Same thing, just the slides are really great, easy to follow. I like that you took a step further and you went into the abutment design.
Thank you.
Did you end up, I guess, are they going to be vertical abutments?
Yeah.
Or will it be spill through?
It'll be vertical abutments.
Okay. And did you have to assume a rock depth to tie to?
Are you talking about like a geotechnical report?
Yeah.
Yeah, so there were some cavities in the soil, and so we decided to go with like a drill shaft. And for the abutments though, we won't have to worry about any cavities.
Okay, good. No, you did good. The slides were great.
Thank
That's
you.
all I've got.
Yeah, same here, Robbie. I think you did a great job. Again, slides looked really great, easy to follow. It looked like they were very thorough. I'm not going to have much technical to add to it, but good job.
Thank you.
All right, so about 10 minutes left. So I am going to start with you, Dr. Huff, and then Dr. Transfer, you'll be next. Because they ask a lot of transportation questions, so we'll let them have more this time. So who would you like to see?
Ethan.
Do you want me to go up or?
You don't have to. Slide 48 was the
existing bridge. Go ahead and go up so that you're on the camera for the remote audience. That's the existing bridge. I see a whole lot of piers in the water there.
Yes, sir.
You got a surface, 100-year elevation 488. Now go to the new bridge. I see 5 piers in the water.
Mhm.
But yet the water's like you're raised, you got 2 feet of backwater. If I were a landowner upstream, I would be calling my congressman trying to stop this project. Can you explain what's causing that 2-foot difference?
I think what was causing it was I had rerun a flow analysis, and it had given us the 490 feet, and me and Sarah had discussed it, and we had tried to figure out why it was doing that, because as you said, you're taking out a lot of piers, a lot of obstructions. So I can't give you a correct answer on that.
It's something to be aware of, but that
Yes.
would be pretty alarming to somebody
Yes.
looking at those lines. Let's see, Kayla. Slide 59.
$59?
59.
Okay, sorry.
Can you explain why you use the larger spacing on the top?
The top map,
Yeah,
We-
12-inch spacing on the top part, and which spacing on the bottom.
I assume we need a higher moment capacity.
Sounds
or-
like a something.
Sorry, I was talking. There'd be a higher moment for the,
I got into somebody's Zoom meeting.
can I mute them?
Remote audience, please remain muted unless you're gonna ask a question in a minute. Actually, that's the one that, okay, yeah.
Is that okay?
Yeah.
Okay. I assume the bottom part of the deck needs to resist a higher moment, and we'll need a higher moment capacity.
Those bars are really carrying tension in and out of the page. They would both be stressed fully to yield. And just exactly the opposite of what you would normally see is a tighter spacing on that layer closest to the tension surface. So that's something that you want to look at. And if you get a chance, look in my comments in your final report.
Okay. Okay.
Maybe one more before we go to Dr. Yes, one more. Robbie, you don't have to, well, you can go up there, you don't have to. It's just about the piles. What was your design criteria for those piles?
Could you elaborate on the question? Sorry.
You used 7 piles, and you said you estimated the total load on the abutment, and that required 7 piles. How did you determine 7?
Okay, so we used HP 12x53s. Those were the piles that we selected. And taking 25% of that yield and multiplying by the area of those piles, we then took the total vertical load of total vertical service load and divided by that 194, which we got from the area of our piles multiplied by 25% yield. And that's how we determined 7 piles were needed.
Perfect, thank you. You guys, all of you did a really good job. You did a really good job speaking. Very impressive. Dr. Vandenberg, 1 or 2?
Sure. So Dr. Huff stole my pile question. So you already answered that. One thing, were the piles included in the substructure cost?
Yeah. Yes, yes.
Okay, I didn't think I saw a line item, but it might have been buried in there somewhere.
Yeah, sorry about that.
I'm just gonna leave it there. Okay.
All right, so parents in the room, friends and family, questions?
The structural team, how do you attach, I guess you're going down to bedrock. You don't have to do no soil analysis or anything. You just, because you're going to attach to rock because it's Tennessee, is that right?
We do need to do a soil analysis, but we would like to attach to rock eventually.
Okay, how do you attach to the rock? You just drill a hole and the concrete goes in, or do you have some kind of pins or, what holds it down, or don't you have to worry about holding it down?
I thought you would do that.
We'll talk later.
These are the answers you get when your parents ask you questions.
I will direct you to Dr. Huff.
I was just curious, what at the bottom, I mean, something has to attach those two, you would think, and I was just wondering how you attach them. That is, okay. Yeah, but
That was beyond the scope of required.
And I was just curious.
Or is it the force and weight of the columns and the bridge itself holding it in place? It doesn't need to ebb and flow up there.
Yeah, that's all.
Is that, I mean, I don't know.
Talking about the footings at the pier.
Yeah, right where the concrete meets the bedrock,
If it's pretty level, you don't need to
you don't need it, it just sits there from the
If
waist
it's
along.
low, you might blast some out to make it level. And occasionally you'll see somebody really concerned about something sliding, and they'll just drill down in some rebar, they punch up into the footing, but typically nothing.
All right, so remote audience, you are also welcome to ask questions at this point. Does anyone want to unmute themselves and ask a question? Going once? Going twice? Going 3 times? Let's give the group a hand. They will all breathe a heavy sigh of relief. All right.